Today's case study tutorial is going to discuss sensitivity testing within Rodel and some of the features that it has that allows for testing sensitivity. One of the primary sensitivity testing is the factor. In your flow modification input area, you have your percent trucks as well as a flow factor, which is just referred to as factor here. It's set at 1 typically. That would represent your traffic that you've entered for the design horizon. That factor can be modified up or down to increase or decrease the percent of traffic for a specific approach and do specific testing. You can test for what if a development has more or less traffic generation. What if trip generation on the long range traffic is a little bit less or a little bit more? And so it's a nice feature that it also can be used to, if you know your annual percent growth, you can easily test for a mid-year, a mid-horizon, say a 10-year horizon scenario. So in this first project, I have the Rodel. The traffic's loaded for the long-range traffic condition, and as we run it, you can see our level of service is quite high, long-range traffic, which ordinarily it's great. Level of service A, we have one. Level of service C, this is unsignalized thresholds. But that's an indication that you have likely opportunities to reduce laneage, and so you'll want to look at that a little closer. This is the original design and the original laneage. You can see we have a 3-lane entry southbound, 3 lanes for leg 2. For eastbound, we have a 2-lane entry northbound and a 3-lane entry westbound, and that gives very high levels of service. So as we start to look at Rodel, one of the first things we did was in this project was look for opportunities to, with that long range flow, are there safer geometrics? So one of the things we've done, first of all, is just at a conceptual level, add a raised auxiliary island to separate right turns from the through traffic. That can allow you to improve safety, improve your speed control within the design. So then what we did was, from there, we went ahead and reduced the laneage. So for example, for the what I'm going to do is open up the other interim geometry. So what we've done is we've modified this geometry to reflect single lane approaches for the southbound leg, the eastbound, northbound, and maintain we have a 2-lane approach westbound, so that stays the same. And we've reduced the entry down to single lane entries for the first 3 legs, so southbound, eastbound, as well as northbound. And again, westbound is fixed at 2 lanes in this case. And we've modified other geometry accordingly for that project. The traffic is the same. We're looking at the same horizon hour, truck percentage, and in this case we've not adjusted the factor, the traffic factor at all. But as we hit run, what we find with this reduced geometry, reduced laneage geometry, we look at our level of service and look at our VC ratios and our delays and our queuing, and we can see that we're getting still acceptable levels of service for long range flows, with D being the worst, which is that eastbound approach as a single lane entry with the yield right turn lane. And so it's a very good indication that that this what we may call an interim geometrics would in fact produce acceptable performance operation and level of service for even on the long-term traffic. We're looking at the 60-minute results. We'll change that to the peak 15-minute results here, which still the worst that you have is a D. If we look at that delay, it's 29 seconds of delay. Typical queuing, 6-7 cars. 95% queue is 15 cars. you might look at that approach and ask yourself, is that level of queuing problematic? Are there things upstream that queuing, in the event that queuing occurs, that would be problematic? Will it back into an upstream intersection, or some other sensitive issue? In this particular case, there is nothing sensitive on that approach. So a typical queuing of 15 cars in the long range, which would equate to maybe 350 feet, for a 95% queue is more than acceptable. So it gives a strong indication that we have a significant opportunity to reduce the conflict points by a substantial amount, 42% total reduction. One thing that you can do is, for example, if we know we have 2% annual growth that's built into our long range flows, and we want to test this on a 10-year design horizon, we could simply take 2%, 2% per year times 20 years, a 40% increase, straight line increase. And so if we reduce this by 20%, sorry, so it'll be 0.8%, and hit run. We're again back to a very high level of service. So I'll put this back to 1, and you can correspondingly. So what if the traffic's off? What if we have a 10% increase in that flow? And you can see it's pretty sensitive with a 10% overage over the 2035 flows. That your VC ratio is going up over 1, just barely, for legs 2 and 3. Our delay is going up to 80 seconds and 57 seconds. So it's sensitive. The VC ratio is higher. What if you go up by just 5% of traffic? So it's level service D. So you're sort of you're at the end of life horizon. Things are supposed to be degrading as per our operational criteria, and it is. I'm going to set this back to 1, hit run. So in this case, what we went ahead and did was we set this up as an interim design with the ability to expand if they ever need it. So really they have a design. They weren't particularly comfortable with the long range traffic, or another way to put that is it just gives them, if traffic projections are higher than what we predicted, they're going to have the ability to expand this for additional capacity. So I'll just go back and forth. You can see it's a very seamless transition from this interim to a longer range, more laneage condition. In this next example, it's similar in that this project has you can see, we'll call the north leg 1. It's a 2-lane entry with a right turn lane, so it has, and 3 lanes circulating. So there's 6 conflict points there. There's a 3-lane entry with 2 lanes circulating, so 6 more conflict points with the right turn lane. For the eastbound approach, northbound 2-lane entry, 3 lanes circulating, and then leg 4, which is the westbound approach, has a 3-lane entry with 2 lanes circulating. So there's 33 conflict points, and there's also 20, when you just count the amount of laneage that the pedestrians are crossing, there's 20 pedestrian conflict points. And as we look at the operations that are predicted with Rodel on the long range flows, we have level service A with that long range geometry. So that's your first indication that that was the 60 minutes. I'll check the peak 15-minute analysis period, and still level service A, less than 10 seconds of delay for all approaches on the long range flows. In addition, this project has substantial amounts of traffic growth built into the long-range flows, approximately 87% traffic growth from existing to long range. So that tells you if we construct this long-range geometry, it's going to be substantially overbuilt, or there's going to be more laneage than is necessary for those early years, the mid years, and in this case, even the long term years for this project. So knowing that our operations is showing very high levels of service, knowing that we have a substantial amount of traffic prediction and growth, we start to look at using the sensitivity tools within Rodel. So I'm going to go ahead and pull up another Rodel file where I have the same traffic, but I've modified the geometry, which is illustrated in the exhibit on the left. So now we've modified the geometry to basically two circulating lanes all the way around, and so we're able to reduce the conflict points from 32, I think it was, to 24. As we put that geometry into Rodel, if I'll leave the factor, the traffic as it was, and if I hit run, I'll go to the 15-minute. We can see we have, A and C and B and then F. I have one approach, the eastbound or westbound approach is showing 100 seconds of delay. So that's not really acceptable. But remember, we have 87% traffic growth built in over the 20-year period. So if we were to just, for example, say, what if we take 10% traffic off that long range traffic and say, what happens then? And we can see with a 10% reduction that we are getting acceptable levels of service with this interim geometry shown at a sketch level service C, and the other legs are at level service A in this case. So I'm only illustrating one peak hour, and of course you're going to have directional traffic, and you'll have to analyze both peak hours to check things through. So in this case, we recommended an interim design that allowed for a safer geometric layout for the near term, mid-term, and moving into the long range flows as well, with the ability to then expand and add a third lane when and if necessary for that westbound entry. And this concludes the sensitivity testing. Thank you.